I'm the speaker. My name is Ricard Bejarano. I'm a site reliability engineer at Cisco and one of my squad's duties basically is to look over our Terraform pipeline, how we get changes into production. Well, the system that does it, the CI/CD of it, is our responsibility. So before I begin, I'd like to get a little bit of a sense of the room. Who's using Terraform these days for work? Now keep your hands up. Are you using it for more than 1,000 managed resources? 10,000? 100,000? Okay, hand there. Good. This starts being useful, the performance improvements I'm going to describe, starting at 20 to 30,000. For context, this is our scale. We have around 120,000. It's not that much compared to the biggest users out there, but we do get a lot of changes. We do get a lot of operations per second, and that really puts a strain on the CI/CD system that runs all these changes. So everything I'm going to talk about is already written down. You don't need to take notes. I have a blog post about it on April. I'll share the link later as well, so no need to take a picture of it right now. But yeah, let's run through real quick what an average plan or change with Terraform looks like. So let's put it on a timeline. We first need the system to fetch the code, the Terraform code you wrote that you checked out. And then we enter into the init phase. That needs to read state off of S3 or wherever you got it. Then you need to fetch the module, so that is other code that you reference so that you can reuse it externally from somewhere else. Then you need to fetch those providers. Once you have all of the code that you use, you know what providers you're going to need, and so you need to fetch those binaries as well off of the Terraform registry. And that is basically all of the init phase. Now, then you go into planning. When you plan, you need to, again, read state again. You need to now initialize these providers. Initializing the providers basically are just a binary that runs on the system right next to Terraform as a separate process, and Terraform talks to it. That standard RPC model is what allows Terraform to be extensible without recompiling Terraform itself. So you need to start those daemons so that Terraform can talk to them. Then you need to refresh state. You're probably familiar with this if you have a very big state, because this has been annoying you for a while. It's basically going out to the provider's APIs and updating state so that the state is an up-to-date picture and not whatever it was last time you applied. Then you diff, which is comparing the current actual updated state with what you want state to look like, and the output of that is the plan, what we typically call the plan. And then you just write the state to lock that state as the latest, that diff as the latest diff, so that if someone else plans, you know that that plan is stale. Then you have a human review it, hopefully, and then you enter the apply phase, in which you re-init providers, because it could be a long time, you don't want to keep those up for as long. Then you apply, and finally you write the state that you've written that state. That is the full timeline of making a change through Terraform. Now let's look at that through the lens of performance optimization, how we can improve this. First, we're going to map out what are the number of network requests that are made on each of these phases. So first, for fetching code, reading state, writing to state, all of those are just one request. And then for fetching modules, that depends on the number of modules. For fetching providers, depends on the number of providers. For refreshing state, that scales with the number of resources that you have in your state. So if you have 1,000, that's 1,000 calls. If you have 1,000,000 resources on a single state, that's 1,000,000 API calls every time you plan. And then for apply time, it matters only as long as you have a lot of changes. So if you have one change, it's only one request. If you have 100 changes, it's 100 requests. Now let's look at those requests and how big they're typically at. So for fetching code, fetching state, writing to state, those are typically in the low megabytes, single digit, 2 digit at most. That's even smaller for refreshing state and applying, because that's typically just a very small JSON blob that represents the object that you're changing or reading on the API provider, so it's not that big. Where it gets hairy, though, is on modules, which are, again, about 10 megabytes, depending on the size of the repo, but providers specifically are terrible. I've seen some that are like 3 gigabytes. The largest I've seen, it was just a one, but it was like 7 gigs. And then the AWS provider, which probably everybody uses, is 700 megabytes last time I checked. So if you have multiple versions of that, you're also pulling that multiple times. So it's a lot of data you need to pull every single time you make a change. And so this results, hand waviness on this, but this results on this sort of performance impact to the user, right? How the user perceives the performance impact of all of these phases based on the number of network requests and their size. So typically, the most painful parts are fetching modules, providers, refreshing state, and then apply. It just depends on how much you're working. So it's sort of correlated with how much they're doing, so they don't care as much. Now let's look real quick at all the available optimization techniques. For fetching modules, you can switch to get modules. That is cool, but it can work, but it has a very small impact. You can only do it once, and then it has a lot of other problems, such as managing those submodules, which if you've tried, you know. So that is one option. Another option is switching to local modules. Similar, putting your modules in like a modules folder and using that. It works, but it's limited to mono repos. So if you have a multi-repo setup, you're not going to be able to reference those modules, or you will, but you will lose out on all the optimization. And again, it also has other problems like what the layout looks like and things like that. And then there's a feature request in Terraform for a module cache, similar to the provider cache, but it's not yet built. It's on that issue number. I hope it gets merged. And then for refreshing state, you can increase parallelism, which is the number of changes that are synced, objects that are synced at a given time. That is faster and that is safe. You should absolutely do that. But it gets to a point where it depends more on the provider rate limits than how much parallelism you give it. You can give it 1 million, but it doesn't really matter because the rate limits are going to be lower than that. And most of the times, those are out of your control, even if you're a paying customer. You can disable refresh, which is the fastest. It completely removes this stage out of the plan phase, but it's also a little bit dangerous. You need to make up for that lack of refresh somehow else, because otherwise you could be making plans on a plan that's changed. If you have someone making a ClickUps change or touching things on somewhere else, you really want to be careful with that. It's unsafe. Then you can do light planning, which has that issue number like linked there. This is an idea that I had like a couple of years ago and that I proposed, and it's just there available for whoever wants to implement it. It's faster, it's safe-ish. The gist of it is basically you make a refresh less, like a refresh equals false plan first to figure out what resources have changed in code, and then you do a refresh full plan with just those resources targeted. So that way you only refresh the resources that you changed in code, which is safe-ish. Again, you still need to check that the full state of it is up to sync with the provider, like on off hours or on weekends or something. But you can do that. It's faster, it works, we do it, it's fine. But it's experimental, it's not even a feature. Right now there's only like a batch one-liner that does it. So your mileage may vary. Then you can break down, this is what typically people do, you can break down a single big state into multiple smaller states. Not only like dev and prod, but also like VPC and EKS, right? This enables parallel operations, which is good. This is safe. It doesn't do anything hacky, but it has way more other problems associated with it, such as how do you communicate dependencies between unrelated states that belong to the same environment. So you may want to make a change to the VPC state, but if that VPC is recreated, it will not get synced up into the EKS state, and it will mess up whatever is in the EKS state, right? So it has a ton of more other problems that we're not going to get into right now. Then for fetching providers, you can consolidate provider versions. You should absolutely do that. If you have 3 versions of the same provider, you should go down to just one, because that's 3 times less download. It has very small impact though, because you can only go so far with it. Again, you can break down a big state into multiple smaller states. It depends on how many providers you use, but if you have an AWS provider and a MySQL provider, you could put the resources in both those separate states, and that would let you download just one provider every time you plan either one of those. Again, the impact is very low. And then you could enable the provider cache. This is the fastest of them all. The provider cache is a built-in mechanism in Terraform that caches the providers, the binaries, but it's not concurrent safe, preventing parallel operations. This is the problem that we're attacking. That has an issue number linked right there. It's on the Terraform repo, but this is what we're going to attack. And the way we're going to do it is through concurrent safe provider caching with OverlayFS. So, oh, by the way, if you want to reduce the apply time, all you can do is just work less. So, Terraform provider cache is not concurrent safe. This has been documented in docs. There's multiple conversations and issues. The answer is it's complicated. It's not coming anytime soon. It's tough to get out of this hole. However, OverlayFS. For those of you not familiar, OverlayFS is a Linux file system. This is the Wikipedia description. They did a way better job than I would do. But it's basically a built-in Linux file system that's used in multiple places. If you've built Docker images, like we were just doing, it's used for each of the layers. Every time you mount a container image, it's actually a union file system, an OverlayFS file system that mounts all of the layers, one on top of each other, and then adds an empty layer writable on top. That's how you have an immutable image with a writable layer on top. If you've used a live CD, Ubuntu Linux or whatever live CD distro, this is what it does. This is how you can write files even though it's a CD-ROM, right? This is how it basically mounts the CD-ROM as the underlying lower dir, and then it adds an upper dir that's writable. So a quick overview of how it works is for each of the operations that you typically do, you have a lower dir, an upper dir, and a mount dir. Lower dir is read-only. This is where the data that's immutable will live in. Upper dir is your writable layer on top. And mount dir is where the illusion of both together is mounted at. So if you read, and there's a file on lower dir, it'll read right through. If you write, it'll only write to upper dir, because lower dir is read-only. If you overwrite a file that already exists, it'll write to upper dir. And then if you delete, it'll just add a delete marker, the same way it happens in S3, for example, if you have it versioned, right? It doesn't actually delete. So the way we implemented Terraform provider caching concurrent safe with OverlayFS is, this is before, so basically with Terraform's provider cache, you have a read-write directory, which you configure through tf-plugin cache dir, the environment variable. And then when you try to do this, if you try to init multiple times at the same time, one will succeed, but all others will fail. With OverlayFS, the way we do it is we have a read-only central cache, which is our lower dir. Then we have per process writable upper dirs. Those are our local caches. And then we mount those respectively at mount dir. And then each Terraform process gets its own mount dir through the use of that variable. This is all automated, we don't do it manually, of course. This is on our CI/CD. But when you try to do this, everything succeeds, because you're not writing twice to the same directory. That's the whole point, that's the whole reason it doesn't work. So looking at how that changes our faces, if we go back to the timeline, we take our fetch providers step, we cut it in half because we now only do, we fetch providers and we persist providers. Those take less time over time because we only need the missing providers. Everything else is cached. So over time the cache fills up and you no longer download providers unless there's like a release or something. So they take way less time. And then you can also move that persisting provider step later after plan when you're waiting for the human to review, which takes significantly longer than any of this, right? And so the overall timeline shrinks. Our results, again, this may vary depending on your scale, but more than 10x faster plans for us, especially after the cache filled up. Basically, and from the user's perspective, for our bigger states, think thousands of resources, we went from measuring in hours to minutes. And for smaller states, a dozen, maybe a couple dozen, we went from like minutes to seconds. It's blazing fast. Also very important, we restored the ability to plan our entire infrastructure in less than an hour. I think this is something that a lot of people are missing, but this is super cool. We get like live drift detection. We can like roll out a new tag to all our resources in 2 hours, like 1 hour plan and another hour of reviewing and making sure it's safe. So it's super cool. And most importantly for me, my squad no longer gets pinged when slow performance happens in the pipeline, which it still happens, but not so much. So how can you get this? I promised, this is the blog. I'm not gonna get into the exact technicals and commands that we use, but like that's the link over there, you can check it out. If you use HCP Terraform, I presented this a couple of weeks ago at HashiConf, but if there's anyone from HashiCorp that can help get this into the product, I'm open to reaching out. I'd love to get that integrated into the product. Otherwise, if you run your own pipeline like we do, Atlantis or your own GitLab CI/CD or whatever, you can just check out the link and see how we did it. And that's it. Thank you all.